Good morning, 1311 chemistry students. This is Dr. Jingbo Louise Liu. Today we start your chapter 3, Stoichiometry of formulas and equations. In this chapter, we are going to spend 2 different lectures to cover 5 topics. The first topic, the moles. We are going to learn definition of the moles, calculation of moles and molar mass, conversion of moles to mass to the number of entities. Point 2. Determine the formula of some unknown compounds. Those compounds can have different types of formulas. We are going to learn empirical formula, molecular formula, and structural formula. And then today we are going to touch base about writing and balancing the chemical equations. Next class, we are going to finish writing and balancing chemical equations, calculate the quantity of reactants, the quantity of the products. This part 4.4, we are going to be more focusing on the molar ratio from the balanced reaction, the chemical reaction sequences, limiting reactants, and product yield. If time permits, we are going to learn fundamentals about the solution stoichiometry. Otherwise, we are going to leave it in chapter 13 about the colligative properties. The first topic, moles. The mole is the amount of a substance that contains the same number of entities as there are the atoms, exactly 12 grams of carbon-12. You use carbon-12 isotope as your standard. Measure 12 grams. This amount is equivalent to moles. When we discussing the number of entities, refers to the atoms, ions, molecules, formula units, and even the electrons. In fact, any types of particles can be used entity as a representative. 1 mole of any substance of any entity contains 6.022 times 10 to 23 entities. Usually I consider this way, 602, 10, 23. This number is called Avogadro's number and is abbreviated as capital N. Capital N represents Avogadro's constant 602, 10, 23. The molar mass. The molar mass can be used capital MM, 2 M's, which is defined as the grams per mole of its entity. This entity again can be atoms, can be molecules, and can be formula units. For any monoatomic elements, such as your neon, sodium, lithium, any of the monoatomic elements, the molar mass is the same as the atomic mass in grams per mole. The atomic mass, you can read it from your periodic table. For compounds, the molar mass can be calculated by sum the atomic mass of the individual atoms. For example, we have a chemical which is called glucose. This glucose has a chemical formula C6H12O6. The molar mass of this glucose is calculated to be 180.16 grams per mole. The molar mass has the unit grams per mole. Personally, I prefer to use 2 capital M, mm, to represent molar mass. In this formula, we can learn the following information, such as you can understand the element carbon, the element hydrogen, and oxygen. What we can learn, the atoms per molecule of this glucose. For carbon, each of the molecule of glucose, you have 6 carbon atoms, 12 atoms of hydrogen, 6 atoms of oxygen. Moles of the atoms per mole of the compound. Assuming you have 1 mole of glucose, you have 6 moles of carbon, 12 moles of hydrogen atoms, 6 moles of oxygen atoms. Atoms per mole of the glucose, you use the number of moles of the atom multiplied by Avogadro's constant. For carbon, will be 6 times 602 10 to 23. Similarly, for hydrogen, you use 12 multiplied by Avogadro's constant, 6.022 times 10 to the power 23. Similarly, for oxygen, 6 times Avogadro's constant. And also, you can calculate the mass per molecule compound. In each of the compound, you have C6H12O6. For carbon, the mass of carbon in each of the glucose compound, you use 6 multiplied by atomic mass of your carbon, 12.01. Similarly, for your hydrogen, 12 multiplied by 1.008, oxygen 6 times 16.00. And you also can calculate the mass per mole of the compounds. Essentially 12 times 6, 72.06 grams per mole. The mass per molecule of the compounds is at the comparison with the AMU. Similarly for hydrogen, so 12.10, oxygen 19.66. You adding all this total mass together, give you the mass of the glucose per mole. It's called molar mass. Interconversion of moles, mass, and the number of chemical entities can be done using these 4 different equations. The grams of mass equals the moles multiplied by molar mass, grams per mole. The moles can be calculated using the mass divided by your molar mass, or the mass multiplied by 1 mole per number of grams. The number of entities of your substances equals to the moles multiplied by your Avogadro's constant. The number of moles can be calculated using the total number of entities divided by Avogadro's constant. For example, we are going to show you how to do the different calculations. This slide showed the moles, mass, number of entity relationship. So this is my favorite chart. I like to put a chart, show myself what's the interrelationship. I'll leave it for everybody to study. Sample problem number 1. Calculating the mass of a given amount of element. For example, you know the moles of silver Ag, which is 0.0342 moles. I want to understand how many grams of the silver are in. Our plan to convert moles to mass, we simply using the molar mass. In this case, because silver is a monoatomic element, you're simply using the moles multiplied by the atomic mass of your silver to derive the mass of silver in grams. Be careful, the mass will be in grams. Our solution, 0.342 moles of silver multiplied by 107.9 grams silver per mole. So you determine the mass of the silver. Sample problem 2. This question is slightly complicated. You are going to be asking to calculate the number of chemical entity in a given mass of compound. For example, nitrogen dioxide is the compound you are going to study. Nitrogen dioxide is a very major component of your urban photochemical smog that formed in the atmosphere when you drive your car to the school and the car exhaust related to the nitrogen dioxide. We call the thermal nitrogen dioxide. My question is, how many molecules of nitrogen dioxide are there in 8.92 grams of NO2? Our plan. We are going to write down the formula accurately for this nitrogen dioxide. And then you calculate the molar mass by the addition of atomic mass together. You sum the atomic mass of each element to determine the molar mass. And then you convert mass in grams to moles. And then you convert the moles to the number of molecules. So this flow chart shows you write down the molecular formula accurately, NO2, and then you divide it by molar mass, convert mass to moles, and you multiply by Avogadro's constant by moles to produce the number of nitrogen dioxide molecules. Our solution, step 1, write down the formula NO2 accurately for nitrogen dioxide. Step 2, calculate the molar mass of nitrogen dioxide. So 1 times the atomic mass for nitrogen plus 2 times atomic mass for oxygen. You find your atomic mass for nitrogen and oxygen from your periodic table. Nitrogen is located in the number 7 element, oxygen number 8. Find the atomic mass. The molar mass for nitrogen dioxide, 46.01 grams per mole. Step 3. Convert mass to moles. Simply use your 8.92 grams of nitrogen dioxide multiplied by 1 mole nitrogen dioxide per 46.01 grams nitrogen dioxide. You simply use the mass divided by molar mass. My calculation is 0.194 moles of nitrogen dioxide. Step 4. Convert moles to the number of molecules. Simply use the moles multiplied by Avogadro's constant. 0.194 moles nitrogen dioxide multiplied by 6.022 times 10 to the power 23 molecules of nitrogen dioxide per 1 mole nitrogen dioxide. My determination is 1.17 times 10 to the power 23 molecules of nitrogen dioxide. Followed by, we are going to determine the mass percent from the chemical formula. Mass percent of the element X equals to atoms of the X in your formula multiplied by the atomic mass of X, divided by the total molar mass of your compound, and then you multiply by 100%. The mass percent of your element equals the moles of your element in the formula multiplied by the molar mass of your element in grams per mole. Or you can also use AMU, that's a relative number. And then you divide it by total mass of your molar mass of your compound. Again, you multiply by 100%. For example, our sample problem number 3, you are going to calculate the mass percent of carbon, hydrogen, oxygen in your glucose. Again, our problem is the glucose C6H12O6 is a key nutrient for generating chemical potential energy in our biological system. What is the mass percent of carbon, hydrogen, and oxygen elements in the glucose? Our plan: find the molar mass of glucose, which you calculate the molar mass based on 1 mole of glucose. And then find the mass of each element in 1 mole of glucose. And then the mass percentage can be calculated using the mass of that element in 1 mole glucose divided by the total molar mass of glucose. And then you multiply by 100%. So similarly in this chart, flow chart, you determine the amount of the element in 1 mole of the glucose. And then you simply multiply by the molar mass or atomic mass of that element. And then you determine the total mass of the element in 1 mole of your glucose compound. And then you divided the total mass of your one element over the total mass of your compound. And you receive the mass fraction, such as 0.45, 0.72, and then you multiply by 100%, convert the mass fraction to the mass percentage. Our solution: 1 mole of glucose has 6 moles of carbon, 12 moles of hydrogen, 6 moles of oxygen. Therefore, you calculate the mass of carbon, hydrogen, and oxygen. 6 moles of carbon in your glucose multiplied by the atomic mass of your carbon. My calculation, 72.06 grams of carbon. Similarly, 12 moles of hydrogen multiplied by atomic mass of hydrogen. Calculate the hydrogen mass in 1 mole of glucose. 6 moles of oxygen multiplied by the atomic mass, 6.00 grams of oxygen per mole. So calculation is 72.06 grams carbon, 96.00 grams of oxygen, 12.096 grams of hydrogen. The molar mass is the sum of these 3 total mass. Mass percentage of carbon, you simply using the total mass of carbon divided by the molar mass of your glucose. And then you receive a fraction. This fraction multiplied by 100%, you produce the mass percent of your carbon. Similarly for your hydrogen, 12.096 grams of hydrogen divided by total mass of glucose per mole. So you receive the mass fraction multiplied by 100%, you retrieve the mass percent of hydrogen. The last one about mass percent of oxygen, you can use 100% minus 39.99 minus 6.7, or you are going to use the total mass of oxygen divided by the molar mass of glucose. Similarly, you receive the mass fraction multiplied by 100%, produce the mass percentage. This is about the mass percentage calculation, and we also have some examples for you to determine the mass of your element based on the mass percentage. If you know the mass percentage, you simply use the total amount of mass to multiply by the percentage. We are going to show you one example. If you have the sample followed from the previous question, so you have assume 16.55 grams of glucose, how many grams of carbon you are going to have. Similarly, you determine the molar mass of glucose, and you determine the mass percentage of your carbon, and then use that mass percentage multiplied by the total mass. The solution, so carbon, you have 6 moles of carbon, totally in 1 mole of glucose, you are going to have 72.06 grams of carbon. You determine the mass of carbon percentage. You simply using 72.06 divided by molar mass. Using this percentage, multiply the total total grams, 16.55 grams. So you can calculate the grams of your carbon. This is the method we are going to determine the empirical formulas. Further, the molecular formula. We have one more key topic about the molecular formula determination. In order to determine the molecular formula, usually we determine the empirical formula. The empirical formula is the simplest formula for a compound that agrees with the elemental analysis. It shows the lowest, smallest whole number of the moles that gives the relative number of the element of the atom of each element present, such as your hydrogen peroxide can have the empirical formula HO. Its molecular formula is H2O2. The molecular formula shows the actual number of the atoms of each element in your actual molecule for the compound, such as this hydrogen peroxide has the empirical formula HO. The actual molecular formula is H2O2. How can we determine this empirical formula and then formula? For example, if you know a sample which composed of 0.21 moles of zinc, 0.14 moles of phosphorus, and 0.56 moles of oxygen, what's the empirical formula for this substance? Our plan: you find the relative number of moles of the elements, 0.21 for zinc, 0.14 for phosphorus, and 0.56 moles for oxygen. And then you are going to divide it by the smallest number moles, such as 0.14, to determine a relative whole number. If it's not a whole number, you convert it to a whole number by multiply by integrals. Step 1, you are going to use the moles of different elements as the subscript to determine a preliminary formula. And then you are going to convert this preliminary formula to your empirical formula by converting these numbers 0.21, 0.14, 0.56 into the whole numbers. Our solution. So here is our empirical formula. Step 1, simply use all these different number of moles for the different elements as the subscript. Usually you put your metal first, your oxygen in the very last. This is a polyatomic compounds. And then you are going to divide it by the smallest number of moles, which in this case is 0.14. 0.21 divided by 0.14, 1.5. 0.14 divided by 0.14 is 1.0. 0.56 divided by 0.14 will give you 4. This will give you formula zinc 1.5, phosphorus 1.0, oxygen 4.0. This 1.5 need to be converted to a whole number by multiply by 2. Therefore, all of these atoms going to be multiplied by 2. So you have your zinc 1.5 multiplied by 2 is 3. Phosphorus 1.0 times 2 equals 2. Oxygen 4 times 2, 8. Zinc 3 P2O8 actually will be zinc 3 parenthesis PO4 parenthesis 2. This is called the zinc phosphate. That's how you are going to determine the empirical formula if you know the moles. Sample problem, another one. So you are going to determine the empirical formula from the mass of the elements. Our problem is an analysis of a sample of an ionic compound yields to 2.82 grams of sodium, 4.34 grams of chlorine, and 7.83 grams of oxygen. What's the empirical formula and what is the name of this compound? Our plan, you are going to find the relative number of each element, zinc, chlorine, and oxygen. Find the number of moles. You are going to use the mass of each element divided by its atomic mass. And then you use the number of moles as the subscript to determine a preliminary formula. And then you are going to change the number of moles into positive integers, whole numbers, to determine the empirical formula. If necessary, determine the molecular formula. Our solution: convert the number of mass into the moles. So you have your sodium 2.82 simply divided by its atomic mass. 1 mole sodium equals 22.99 grams of sodium. The moles of sodium is 0.123. Similarly, convert 4.35 grams of chlorine into the moles. Again, 1 mole chlorine is 35.45 grams of chlorine. You simply use the grams divided by its atomic mass. Calculation again is 0.123 moles of chlorine. Oxygen 7.83 grams divided by 16. The calculation is 0.489. And you are going to use those numbers as the subscript to determine a preliminary formula. And then you are going to divide it by this 0.123 to convert those numbers to the whole number. Sodium and chlorine becomes 1 and 1. Oxygen is approximately 3.98. Your empirical formula will be Na1Cl1O 3.98. This 3.98 can be rounded to 4. So the formula will be NaClO4. This compound is named as sodium perchlorate. Next class, we are going to determine